Good morning, and welcome to Smashing the State Machine, the true potential of web race conditions. Have you ever seen a vulnerability that made absolutely no sense? Something that didn't just leave you wondering, why would anyone code that, but asking, how is it even possible to write code that has that effect? Maybe you even got hold of the source code and stared at it for hours and it still made no sense. And perhaps, if you showed it to someone else, they'd say something like, oh, it must be a race condition. In this session, I'm going to share with you tools and techniques to discover and exploit that kind of race condition. Let's start by surveying what we do understand. What race conditions have you seen or exploited in the wild? Maybe things like transferring or withdrawing more funds than your account is supposed to have. Perhaps applying a single-use discount code multiple times or bypassing a rate limit on a login form or such like. One of my favorites that I found is I noticed that you can reuse a valid reCAPTCHA solution multiple times within a small time window. I reported that to Google, and they were like, well, unfortunately, our system is so distributed that we can't patch this. And as a result, that technique still works on a bunch of websites today. But all these examples have something in common. They could all be classed as limit-overrun vulnerabilities. They're all about doing something more times than you're supposed to be able to. But if you go digging through every post you can find on race conditions, you'll see glimmers of other exploits now and then. You might land on a post called Race Conditions on the Web by Josip Frankovic. In that post, he describes 4 vulnerabilities. They're all really cool vulnerabilities, but 3 of them are limit overruns, and 1 of them is a bit different. He found this vulnerability by accident. It took 2 months for him and Facebook's security team to figure out how to replicate it. And the symptom was that when changing email address, sometimes Facebook would send 2 codes for 2 different addresses in a single confirmation email. Now, I had no idea what could be causing this, but one thing was clear. This wasn't a limit overrun vulnerability. And so last September, 6 years after I first read that blog post, I decided to try and figure out what actually happened. And gradually came to realize that the race condition attacks that we all know and love already are just toy vulnerabilities compared with what else is out there. So in this session, I'm going to show you the true potential of this attack class, tools and techniques to achieve this potential, and case studies and a live demo to show some of the insanity that's out there waiting for you to discover it. After that, I'll share where things can be taken further, how to prevent these attacks, and the key takeaways, leaving 5 minutes for questions. On certain slides, you'll see this mortarboard icon. That just means that I've designed a free online replica of that vulnerability in the Web Security Academy. So you can practice exploiting that technique live online for free. To communicate the true potential of this attack class, I'm going to use a multi-step vulnerability that I found a while back. I logged into a website, and it asked me to select a role before proceeding to the application. So I thought, well, I guess the state machine for the user's role looks something like this, and maybe I can jump straight from the role selection page to the back end and elevate my privileges. But that didn't work, and I concluded it was secure. I mean, look at that picture. It looks pretty secure, right? But this state machine was wrong. Maybe you've already spotted the flaw with it. It's not zoomed in enough, and it's assuming that the GET request to the role selection page doesn't change the application state. And as it so happened, for reasons I don't entirely understand, the application was creating every session with administrative privileges, and then the GET request to the role selection page was revoking those privileges. So by not sending that GET and going straight to the back end, anyone could get admin access. And by failing to zoom in enough, I'd almost missed that vulnerability. But that's okay. You know, that was just my mistake. Everyone knows that multi-step sequences are a wonderful source of all kinds of serious vulnerabilities, and whenever you see one, it's essential to zoom in as much as possible and test every possible permutation of the process. But while researching race conditions, I found myself looking back at this finding and wondering, is this the furthest that we could zoom in, or can we go further still? What if the application had dropped our privileges immediately using a second database statement? There would still be a maybe 1 millisecond time window where every session had administrator privileges, but I would never have discovered it. That's a slightly scary thought, partly because, well, any login form could have that vulnerability. It doesn't need to be multi-step. But more than that, it shows that any HTTP request could be transitioning an application through an invisible sequence of tiny substates that could be enabling serious vulnerabilities. In other words, we all know that multi-step sequences are really dangerous. And with race conditions, everything is potentially multi-step. That is the true potential of this attack class, and now it's time to start hacking things. To discover a substate, we need a collision, and for that we need two requests. One to trigger the substate or race window, and another that tries to access the same resource at the same time. So in the example we just saw, that might mean something like trying to log in and access the admin panel simultaneously. However, there's a major barrier to this very first step, which has plagued this entire attack class for decades, which is network jitter, which randomly delays requests, meaning that the race windows don't line up and the vulnerabilities don't reliably get discovered. To solve this problem, I've developed the single packet attack, which lets you make 20 to 30 requests arrive at the target server simultaneously, completely regardless of network jitter. Under the hood, this technique is all about TCP and HTTP. The previously best-known technique was called last byte sync, and this exploits the fact that web servers won't start to process a request until the whole request has arrived. So by withholding the final byte and putting that in a separate packet, you make the final packet of each request really small and kind of make things a little bit more reliable. But it only goes so far. A couple of years ago, though, I read an academic paper called Timeless Timing Attacks, where they noticed that with HTTP2, you can stuff two entire requests into a single TCP packet. And they were using that for timing attacks. But it occurred to me that this might have some race condition potential. The only issue is that really, thanks to other factors like server-side jitter, you need more than two requests to reliably detect and exploit race conditions. So to create the single packet attack, I just took these two techniques and smushed them together. I'm releasing this in an update to the open source tool Turbo Intruder, landing in 30 minutes' time. And you can go and try it out for yourself. And, well, it's quite an obvious concept, actually, isn't it? But after implementing this, I actually realized someone else had had the same idea and implemented the same thing for a master's project back in 2020, and nobody even noticed. So what is so exciting about this technique? Why did I even try and come up with a fancy name for it? Well, it's because this isn't just some cool implementation trick. After refining the technique over months of research, it now works on all major web servers. I can still fit the entire algorithm on one slide, and ultimately, it brings insane performance in a parcel that's so easy to implement that I think it's going to end up in all major web testing tools. The reason it's so easy to implement is that thanks to some creative abuse of Nagel's algorithm, which is present in all operating systems' network stacks, this technique doesn't require you to code a custom TCP or TLS stack. You can just take a HTTP2 library and bolt this feature onto the site. If you're tempted to make your own implementation, I'd say go for it, and I think Golang's HP2 stack is one of the easy ones to extend in this manner. And I'm really looking forward to seeing where other people take this technique in future. But right now, let's focus a little bit more on the performance. To benchmark this new technique, I repeatedly sent a batch of 20 requests from Melbourne to Dublin, and I measured the gap between the execution timestamp of the first request to arrive and the last request to arrive in each batch. In other words, how close together they landed. Using last byte sync, we saw a median spread of 4 milliseconds and a standard deviation of 3, which is actually not that bad. I think the reason it's relatively low here is that I was using data centers at both ends of this connection. And if you were using Australian consumer broadband, you'd probably see higher jitter. So then, over the same connection, I tried the single packet attack. And with that, we saw a median spread of 1 millisecond and a standard deviation of 0.3. So in other words, these 20 requests traveling 17,000 kilometers were mostly getting executed on the same millisecond on the target server. That makes this technique 4 to 10 times more effective by those metrics, and with one live vulnerability, I was able to replicate it using the single packet attack in 30 seconds, and it took 2 hours of automated attempts to replicate the same issue using last byte sync. If you want to kind of visualize what this impact actually means, basically, the single packet attack makes remote race conditions local. Now that we've solved network jitter, it's time to go hunting for bugs. Now, limit-overrun vulnerabilities are really easy to find. You look for a limit, and then you try and overrun it. But as soon as you go beyond that to multi-step style attack, things are not so simple. But after months of manual testing and discovering every possible pitfall, I've developed the following 3-step methodology to find these bugs efficiently. First, you predict where you might have potential collisions. Then you probe those places to identify clues as to whether there's a substate there or not. And finally, you prove the concept by figuring out what happened and using that knowledge to build an exploit. Prediction is about efficiency. In theory, we ought to test every possible combination of endpoints on the entire website and also on related websites that share the same backend, which is not very feasible. So instead, we're going to home in on places that are likely to have collisions that have serious consequences, and then try and furthermore rule out endpoints that don't have much collision potential. For example, if you've got 2 threads editing a single piece of data, that might have a collision, whereas if the 2 links are just appending to the same data structure, that's less likely to have an exciting outcome. Likewise, you can ask, well, are our 2 requests going to edit the same record in the database? If a password reset system is storing tokens in the users table, then resets for 2 different users are going to edit 2 different rows of that table, and we're not going to get a collision, and it's probably not worth testing. Meanwhile, if they're doing something like generating a pin and storing it in the user session, then we can use our single session to cause resets for 2 different users at the same time, and maybe a collision and an interesting outcome will occur. After we've built these requests, it's time to use them to probe for clues. So the first step here is to make sure that we recognize a clue when we see one by benchmarking how the application behaves when we don't trigger any race conditions, just by sending the requests to the server one at a time with a delay between each and recording what happens. Then you just throw them at the application all at once and look for any anomalies in how the application responds or behaves afterwards. If you don't get any, that might mean that they're secure or that you need to tune your attack timing, which I'll talk a little bit more about in one of the case studies later. Once you've got an anomaly, it's time to understand what happened, make sure you can replicate the behavior, trust me, that's worth doing, and explore the impact. A word of warning about the impact. If you're doing this methodology right and being sufficiently ambitious, then you'll often end up with behavior from the application that's quite weird and unfamiliar with what you might have seen with other exploit techniques. And as a result, the path to maximum security impact may not be obvious at all, and it can be easy to underestimate it. To try and identify the impact, I would say think of what you found as a structural weakness and see if there's any functionality within the application that this structural weakness undermines. Also, don't just stop and report the first viable exploit that you find. I made that mistake myself and lost out on around $5,000 as a result. Now we're going to look at some case studies. So this is a tiny slice of what you might find if you apply this approach in the wild. GitLab lets you invite unregistered users to administer projects via their email address. And this sounded juicy, so I thought I'd test it out. As a baseline, I invited one address 6 times sequentially, and that resulted in 1 invitation being created, 1 invitation email, and 6 responses saying status success. When I retried this, sending the requests in parallel with the single packet attack, we got 1 status success, 5 error messages, and 2 emails. So there's 2 clues here that we've hit a substate. The first is 2 emails is obviously quite suspicious. And the other one is that the responses that we got differed from what we saw in the baseline. It's worth noting that if we hadn't bothered to do the baseline, then the responses that we got when we did the attack wouldn't have looked suspicious at all, and we might have missed the bug. Now, I initially thought that this had 0 impact, but then I noticed that on GitLab, the page there that lists active invitations assumes that there's only 1 invitation present for a given address. But with this, you can create multiple, and what that means is if an admin sees an invitation that they don't like, they might revoke it, and it will say, user was successfully removed from project. But thanks to this technique, it will actually upgrade that invitation to a better admin level invitation. Now, that impact isn't that amazing because you need quite high privileges to exploit it in the first place. But it got my attention firmly fixed on GitLab. And it left me wondering, well, is there another angle I can take to get a more notable impact? One approach that you can take to finding inspiration for advanced race condition attacks is to look to classic multi-step exploits and see if there's a race condition adaptation. There's one attack where you add an extra product to your basket during an online checkout when you're doing the payment process. And if you time it right, then you get the extra item for free. And I noticed that if you draw the state machine for GitLab's email verification process, it looks quite similar. So maybe if we change our email address while GitLab is validating our previous email address, it'll end up validating the wrong one. That would be high impact because it would let me obtain validated email addresses belonging to other people and, crucially, hijack any pending invitations, like administrator invitations, intended for those other users. So I tried this attack out, and it didn't yield any clues. But I noticed that the email change response was arriving before the confirmation response every single time, presumably because one was a slower operation than the other. And on GitLab, I was able to fix this and get a 50-50 distribution by adding a 90 millisecond delay before I sent the request that was faster processing. So what that meant was that I'd lined up the race windows, and if there was a bug, I was more likely to find it. There's an issue with using client-side delays like this, though, which is that it rules out the single packet attack and means that network jitter might mess up your attack. But I later discovered an alternative solution which is often more effective. Web servers often delay requests that are sent too quickly. And that means that you can send a single packet with a whole load of dummy requests in the middle of it, which will cause a server-side delay and mean that when your fast processing request at the end is reached, it lines everything up perfectly. So because with this, everything is reaching the server at the same time, and the server is injecting the delay for us, network jitter is no longer going to make our attack fail. Using this technique on GitLab revealed a massive clue. Sometimes the email confirmation token was sent to the wrong address. Unfortunately for me, this initially looked really exciting, but this misdirected code was only valid for the address that I'd already confirmed. So it was completely useless. But it did show that there was at least one substate hidden inside GitLab's email change endpoint. And so it was clearly worth digging further. And with that, it's time for a live demo. So here we've got GitLab. This is a remote GitLab installation hosted in Ireland, and I'm going to use the conference Wi-Fi to demonstrate a race condition attack on it, because the single packet attack is so powerful, there's no way that this could go wrong. So I'm just going to demonstrate if I change my email, then the new email is set as pending, because I need to click the confirmation link and prove that I own that address. So I'm going to get the request, and I'm going to send a probe. So the single packet attack is implemented in Turbo Intruder, and for my probe, I'm just going to tell GitLab I want to change my email address to 6 different email addresses. And this is going to happen in the same millisecond on the server, hopefully. And we'll see if anything interesting happens. So the responses should appear all at once. Yep, that looks good. First thing to point out is there's a kind of a tiny hint here. This runtime is pretty low for an endpoint that we know is sending an email. So it kind of suggests that maybe GitLab is passing the email send off to a different thread. And as soon as you've got different threads involved, race conditions get a lot more likely. So if you see that, it's worth doing thorough testing on that endpoint. But for a proper clue, let's have a look at our emails and see if one has arrived. So right, here we go. OK, so you can see this email was sent to demo3@portsrigger.net. But this link is going to confirm demo 5. So that's our clue that something is not quite right here. But it's not a valid exploit because this token is definitely not going to work because it's been overwritten by one of the other requests and some other reasons. So I finished the probe stage, and now I'm going to try to exploit this vulnerability. So I'm dropping down to 2 synchronized requests here. The first one sets an email address that I control, and the second request sets spoof.localhost, which I don't control. That should not be routed to my inbox. There's one other thing worth mentioning, which is that in order for the misrouted token to be valid, you need to trigger GitLab's resend token functionality, not their send token functionality. So you have to preset it to the email address that you control first, so that this one triggers a reset. It took me 3 months to figure that out. So now I'm going to run this, and if we're really lucky, then in my inbox we'll see an email for spoofed@localhost. Maybe this one. OK. I'm just going to try this like a couple of times. It usually works within like 3 attempts, maybe. do have a backup video, but I'm sure it won't be necessary. What this is doing is it's proving the point, right? You use loads of requests to probe for clues, because the more requests you use, the more likely things are to line up and make something interesting happen. Whereas for an exploit, you have to use a tiny number of requests, which makes the whole thing less. All right, so that's promising, but that's a good start, but we still don't know if this lit button is actually going to work. It depends on what happens server side. It worked. Excellent. So you can see my email is now spoofed at localhost, and if we go over here, it shows as verified. And if there was a pending admin invite for that address, I would have just hijacked it. So, oh yeah, one other thing about that bug. I discovered that on gitlab.com, and I couldn't resist using it to get a verified email of albinowaxed@gitlab.com. And you can still see that email on my GitLab profile over there. So that shiny finding left me wondering about what the underlying code might look like. And the vulnerable code path starts out in a Ruby on Rails framework called devise. And the root problem is an inconsistency between how they decide where to send the email and what to put inside it. The email is sent to an address held in an instance variable that's passed directly to the background thread that sends the email. But the contents of the email are generated via a server-side template engine, which reads the security token back in from the database. So the value in the database might have changed in that intervening time period of maybe 1 millisecond, and the wrong token can get sent. The impact of that discrepancy is pretty significant. So as I mentioned, you can use it to hijack invitations, but it's not just limited to that, because GitLab can be used as an OpenID provider to create a sign-in with GitLab button on third-party websites. And depending on how the third-party website implements that feature, that vulnerability can enable issues all the way up to arbitrary account hijacking on the third-party site. Just to mention, if you were to find that bug in one of the major OpenID providers, that would be pretty cool. I did look for it, I didn't find it, but that doesn't mean it's not there. I reported this issue to GitLab, and they patched it pretty quickly. And then I confirmed it works on other websites using the devise framework, and I reported it to devise, and that did not go so well. I reported it to 4 different addresses over the span of 200 days and heard absolutely nothing back from them until last week. So we know they are now looking at it, which is good, but I do not believe a patch is available yet. Now, this library is really popular. It's also really easy to fingerprint because there's a fingerprintable unauthenticated endpoint at /users/confirmation. And because it's a library, the way every website integrates with this functionality is slightly different, so exploiting it is kind of different and fun every time. A few of the highlights that I found looking at bug bounty sites that use devise were some sites are secure because they have visible locking around the whole email change process. They obviously only process one email change request at a time. On another site, when they generate the confirmation email, the email doesn't tell you which email address it's going to confirm. So there's no clues that the vulnerability is present. And to actually exploit that, I had to write a script that repeatedly triggered the emails, received the emails, parsed them, visited the link, and then reloaded my profile in order to work out which email address actually got confirmed. And on a couple of other sites, their visible email change functionality was secure, but devise registers a hidden endpoint for resending emails, and that endpoint was still vulnerable. And with that, it's time to move on from GitLab and devise. Now, Race conditions are weird, and I've saved the weirdest one for the last case study. This was another token misrouting flaw, but the two email change requests could be sent with a 20-minute delay in between them. And you might be thinking, well, that doesn't sound like a race condition. But it was reliably inconsistent, just like you would expect a race condition to be. And after some analysis, what I think was happening is that my email change requests were getting put on a queue, and that was being processed by a multi-threaded batch job once every 30 minutes or so. So my request timing was almost irrelevant. The reason I triggered the vulnerability was my request volume. And the only reason I discovered it was that I noticed that I received 2 emails to the same address. So basically, these second-order clues, like the emails you get afterwards or the state the application ends up in, are absolutely crucial for finding deferred race conditions like this. You can't look at the response the application sends you, because when it sends you the response, the race condition hasn't even been triggered yet. Overall, over the course of this research, I've begun to regard spotting anomalies like this as probably the most important skill for finding race conditions. Now, for my case studies, I focused on email-based attacks, but there's quite a few other places where you can find high-impact race conditions. One pattern you'll find is partial construction vulnerabilities. These are particularly likely when an object is created in multiple steps, creating an insecure middle state, like in this code snippet here, which is some code that I wrote 5 years ago that was not supposed to be vulnerable. There's a brief window where this token value is not initialized. Now, this type of attack is most likely to work on applications that have default or null type values and that don't just throw an exception when they encounter those values. But that attack isn't that scenario is not a strict requirement for this attack. And for a completely different type of partial construction attack, check out the linked vulnerability found by Natalie Silvanovic in Google's WebRTC implementation. Now, another angle for further research is to explore the root cause of race conditions, which is unsafe combinations of data structures and locking strategies. There's 3 main strategies that I've run into. The first one is the classic defense, which is locking. For example, PHP's default native session handler only processes one request in a given session at a time. Now, that means that, well, a site isn't going to have a session-based race condition with that session handler. But even if it has a database race condition, if you try and exploit that with a single session, you're going to fail to find the vulnerability. So it's important to spot this locking behavior and adapt by using requests in multiple separate sessions for your attack. The second approach is batching, which is really common in most modern session handling mesh systems because the performance is pretty good. This is where they read the entire value, like the entire session from the database into a local in-memory copy when they get your request. They apply any read and write operations to that copy, and then they write the whole thing back to the database at the end of the request lifecycle. That makes them internally consistent with regard to that thread during the request lifecycle. But as we saw on GitLab, as soon as data gets passed to a background thread, everything falls apart. Also, if you've got 2 requests operating on the same record at the same time with this system, then generally one of those requests will end up overwriting the database changes from the other. Finally, sometimes there's no defense at all. So we see this with databases where transactions aren't being used, and you will occasionally see this with session handlers, especially custom session handlers. Now, if your session handler falls into this category, that's quite bad news because there's loads of plausible, completely reasonable code patterns that are absolutely fine unless your session handler isn't doing batching, in which case they suddenly have critical vulnerabilities. So it's worth making sure that you know what approach your session handler is using. The final area for potential improvement is, of course, improving the single packet attack. So currently, my implementation lets you get 20 to 30 requests reliably in a single packet, and I'm certain that you can fit more in. You can definitely do it with a custom TCP or TLS stack, but that's probably a bit of a pain to implement. But there may be other easier strategies that exist as well. I'm confident this can be pushed further. I didn't look into it in depth myself because once I got 20 requests in a single packet, that was enough to trigger enough vulnerabilities to be getting on with. The other thing that would be improving, the other thing that would help is finding ways to cause delays of different lengths of time reliably server-side using that technique, because that would mean you could use it to try and find a broader range of vulnerabilities that require different timings, and it would also help out with certain timing attacks as well. Now, as far as defense goes, when a single request can push an application through multiple invisible substates, understanding and predicting that application's behavior is incredibly difficult, and defense is really not practical. So I would suggest trying to avoid the creation of substates wherever possible, and the way to do that is primarily to use your data store consistency features and avoid mixing data sources. Devise was vulnerable because they read a token from the database and sent it to an address held in an instance variable. If they'd passed both values in instance variables, they would have been fine. Or if they'd held them both in the database, that would have been fine too. It was this blending that led to the vulnerability. The other key point for defense is, of course, make sure you know what locking strategy your session handler is using. Now, there's quite a lot of further reading available. I would primarily like to suggest check out the white paper. That's the online version of this presentation. It'll be live on our website in 2 minutes' time. Have a practice on the online labs. They're free, and there's no substitute for getting actual experience exploiting these vulnerabilities. And then finally, grab my code and go out and find some real vulnerabilities in the wild. There's a lot of them out there. I've left more on the table than usual because I wasn't able to automate scanning for this type of issue. And if you have any crazy findings with these techniques that you'd like to share, I'd definitely love to hear about it. The 3 key things to take away are the single packet attack makes race conditions reliable. With race conditions, everything is potentially multi-step, and to find these bugs, predict, probe, and prove. I'm going to take 3 minutes of questions now. If you have any more after that, feel free to come and chat to me at the back, or just chuck me an email. Don't forget to follow me on Twitter or wherever you are these days. Thanks for listening.